Practical applications of Bayes' theorem. Welcome, everyone. Now that we have spent some time in our previous lessons exploring the mathematical formulation of Bayes' theorem, essentially learning how to manipulate the formula and understand its components, it is time to move beyond the abstract. The true power of this theorem doesn't just lie in the algebra, but in its application to real-world scenarios. What makes Bayes' theorem so unique is that it allows us to perform what we call inverse probability calculations. In simpler terms, instead of predicting an outcome, we observe an effect, which we call the evidence, and then we work backward to determine the most likely cause or the hypothesis behind that evidence. This ability to work backward is incredibly important. It is a fundamental tool in critical fields such as medicine, engineering, and law. In these professions, professionals rarely have a complete picture. They must make high-stakes decisions based on incomplete or probabilistic information. Over the next few slides, we are going to look at exactly how this works through some practical examples. Medical diagnostics. Now that we have covered the mathematical formula in the previous section, let's look at where this actually matters in the real world. One of the most critical applications of Bayes' theorem is in the field of medical testing. I want to highlight a very common misconception that even many adults fall into. Imagine you are told that a specific diagnostic test for a disease is 99% accurate. If a patient receives a positive test result, the natural, intuitive reaction is to assume there is a 99% chance they actually have the disease. However, as we are about to see in our next example, this logic is often flawed. The reason is that this assumption completely ignores what we call the base rate, which is simply how common or rare the disease is in the general population. To understand why this distinction is so vital, let's move on to our first worked example involving a rare disease. Example: testing for a rare disease. Now, let's move from the theory into a concrete example to see how this works in practice. Imagine we are looking at a medical scenario involving a very rare disease. First, we have our base rate, or the prevalence. Suppose this disease affects only 1% of the general population. Next, let's look at the reliability of our diagnostic test. We are told the test is 99% accurate for those who actually have the disease. We call this a true positive. However, it is also 95% accurate for those who do not have the disease, which is our true negative rate. Here is the critical question we need to answer using Bayes' theorem. If a patient walks in, takes the test, and receives a positive result, what is the actual probability that they truly have the disease? It might intuitively feel like the answer should be 99%, but as we are about to see in the next slide, the math tells a much more surprising story. Step-by-step breakdown: medical diagnostics. First, we need to define our hypotheses, which we call the partition. This is just a fancy way of splitting the entire population into two mutually exclusive groups. Let E1 be the event that the person actually has the disease, and let E2 be the event that the person does not have the disease. From our previous slide, we know the prevalence, or the probability of E1, is 0.01. Since these are the only two possibilities, the probability of E2 must be 1 minus 0.01, which gives us 0.99. Second, we define our observed event. We'll call this event A in this specific case. Event A represents the moment we see a positive test result. Third, we need to identify our conditional probabilities, also known as the likelihoods. We are looking for the probability of event occurring, given that a specific hypothesis is true. First, the probability of testing positive given the person has the disease, that is, the probability of a given E1, is 0.99. Next, we look at the probability of testing positive given the person does not have the disease. This is a false positive. Since the test is 95% accurate for healthy people, the chance of a mistake is 1 minus 0.95, which equals 0.05. Fourth, we apply Bayes' theorem. Our ultimate goal is to find the probability of E1 given A. In other words, the probability the person is actually sick, now that we have seen that positive test result. To do this, we use the formula where the numerator is the probability of E1 multiplied by the probability of a given E1, and the denominator is the total probability of testing positive. This total probability is calculated by summing the probability of a true positive and the probability of a false positive. Finally, let's substitute our values into the formula to get the result. In the numerator, we multiply 0.01 by 0.99, which gives us 0.0099. In the denominator, we take that same 0.0099 and add it to the probability of a false positive, which is 0.99 multiplied by 0.05, resulting in 0.0495. When we add those together, we get 0.0594. Dividing 0.0099 by 0.0594, we get approximately 0.1667. Now that we have the scenario laid out, let's walk through the mathematical breakdown step by step to see how we actually reach our answer. As you'll see on the next slide, this result is quite surprising given how accurate the test seemed at first glance. Conclusion: Medical Diagnostics. Now, let's take a moment to reflect on that result. It might feel quite counterintuitive, doesn't it? We started with a test that we described as being 99% accurate for those with the disease, yet our final calculation shows that the probability of the patient actually having the disease is only about 16.67%. It seems like a massive gap, but there is a very logical reason for this. The reason the probability remains so low is due to the base rate we discussed earlier. The fact that the disease is incredibly rare, affecting only 1% of the population. Because the disease is so uncommon, the number of false positives from the healthy 99% of the population actually outweighs the number of true positives from the tiny 1% who are sick. This brings us to a vital lesson in probability. Always consider the rarity of an event before jumping to conclusions based on new evidence. Now, let's see how this same logic applies to a different field: industrial quality control. Quality control in manufacturing. Moving on to slide 6, let's look at another vital application: quality control in manufacturing. In large-scale industrial settings, products are rarely made by just one source. Instead, they are often manufactured by multiple different machines working simultaneously. This creates a challenge. If a quality inspector pulls a product off the line and finds a defective item, how do we know where the error originated? This is where Bayes' theorem becomes an incredibly powerful diagnostic tool. It allows us to work backward from the observed effect, the defective item, to identify which specific machine is most likely responsible for the fault. Now that we have seen how Bayes' theorem applies to medical diagnostics, let's shift our focus from biology to engineering. Example: defective bolts. Now that we've seen how Bayes' theorem applies to medical testing, let's shift our focus from biology to industrial engineering with a practical example involving quality control. Imagine a factory that uses 3 different machines. Let's call them Machine 1, Machine 2, and Machine 3 to produce bolts. Each machine contributes a different amount to the total stock, and each has its own error rate. Specifically, Machine 1 produces 50% of all the bolts, but 3% of its output is defective. Machine 2 produces 30% of the bolts, with a 4% defect rate. Finally, Machine 3 produces the remaining 20%, and 5% of its bolts are defective. Now, here is the problem we need to solve. Suppose we reach into a bin, pick a bolt at random, and discover that it is actually defective. Given this piece of evidence, what is the probability that this specific defective bolt was produced by Machine 1? To solve this, we'll need to use the systematic approach I'm about to show you in the next slide, where we'll break these percentages down into formal probabilities. Step-by-step breakdown: quality control. First, we need to define our hypotheses, which in this case is the partition of all possible causes. We have 3 machines, so we have 3 events. Let E1 be the event that the bolt was produced by Machine 1 with a probability of 0.50. Let E2 be the event it came from machine 2 with a probability of 0.30. And finally, let E3 be the event it came from machine 3 with a probability of 0.20. Second, we must define our observed event, which we'll call event A in this specific problem. Event A represents the fact that the bolt we have drawn is actually defective. Third, we need to identify our conditional probabilities, or the likelihoods. These are the error rates for each machine. The probability of a bolt being defective, given it came from machine 1, is 0.03. For machine 2, the probability of a defect is 0.04, and for machine 3, it is 0.05. Fourth, we apply Bayes' theorem. We are looking for the probability of E1 given event A. To do this, we take the probability of E1 multiplied by the probability of a given E1, and then divide that by the total probability. The denominator is the sum of all possible paths to a defect. The probability of E1 times the probability of a given E1 plus the probability of E2 times the probability of a given E2 plus the probability of E3 times the probability of a given E3. Finally, let's substitute our actual values into the formula to get the result. In the numerator, we have 0.50 times 0.03. In the denominator, we calculate the sum of all three scenarios, 0.50 times 0.03 plus 0.30 times 0.04 plus 0.20 times 0.05. This simplifies to 0.015 divided by the sum of 0.015, 0.012, and 0.010. This gives us 0.015 divided by 0.037, which results in approximately 0.4054. Now that we have the scenario for our defective bolt, let's walk through the mathematical breakdown step by step to find our answer. As we will see in the next slide, this tells us exactly how much we should suspect machine 1 is the culprit. Conclusion: quality control. So, let's take a look at what this result actually tells us. After performing all those calculations, we have found that there is a 40.54% probability that the defective bolt was produced by machine 1. Now, you might notice that even though machine 1 produces the largest share of our total bolts, the probability isn't overwhelmingly high. This is because we have to balance the high production volume of machine 1 against its specific error rate, alongside the error rates of the other two machines. Moving forward, we can use this same logic to see how Bayes' theorem applies to entirely different fields, such as forensics and evaluating the reliability of information. Forensics and truth-telling. Now that we have seen how Bayes' theorem applies to medical diagnostics and industrial quality control, let's shift our focus to a completely different field: forensics and the evaluation of truth. In legal or investigative scenarios, we often have to deal with testimony or evidence that isn't 100% certain. Bayes' theorem provides us with a mathematical framework to evaluate the reliability of a witness or any specific source of information. Essentially, it allows us to take a piece of reported evidence and determine how much we should actually trust it, based on how reliable that source is and how likely the event was to happen in the first place. Let's look at a concrete example of this in the next slide. Example: the reliable witness. Now that we've seen how Bayes' theorem applies to medical testing and manufacturing, let's move into a more forensic context, specifically looking at the reliability of information. On this slide, we have a scenario involving a witness to an accident. Imagine a witness claims that a car involved in a crash was blue. Now we have two pieces of information to consider. First, we know the witness's track record. They are known to be correct 80% of the time. Second, we have the base rate, or the background information for this specific city. Only 10% of cars in this city are blue, while the remaining 90% are other colors. Our mathematical challenge here is to determine the following. If the witness has just reported that the car was blue, what is the actual probability that the car was, in fact, blue? As we move to the next slide, we are going to break this down step by step. just as we did with the medical and factory examples, to see how that 80% reliability interacts with the rarity of blue cars. Step-by-step breakdown, forensics. First, we need to define our hypotheses, which is what we call our partition. We have two mutually exclusive possibilities here. Let E1 represent the event that the much car is actually blue, and based on our previous slide, the probability of E1, or the prior probability, is 0.10. Conversely, let E2 be the event that the car is not blue. Since these are the only two options, the probability of E2 is 1 minus 0.10, which gives us 0.90. Second, we define our observed event, which we will call A in this case. Event A is the specific piece of evidence we have just received, the witness reporting that the car is blue. Third, we need to identify our conditional probabilities, also known as our likelihoods. We know the witness is 80% reliable. So, the probability of the witness saying the car is blue, given that the car is actually blue, is 0.80. However, we must also consider the chance they are mistaken. The probability of the witness saying the car is blue, even though the car is not blue, is 1 minus 0.80, which equals 0.20. Fourth, we apply Bayes' theorem. We are looking for the probability of E1 given event. A, the formula, is the probability of E1 multiplied by the probability of a given E1, all divided by the total probability, which is the sum of the probability of E1 times a given E1, plus the probability of E2 times a given E2. Finally, let's substitute our values into the formula to get the result. In the numerator, we have 0.10 times 0.80. In the denominator, we have that same 0.08, added to the product of 0.90 and 0.20. This simplifies to 0.08 divided by the sum of 0.08 and 0.18. That gives us 0.08 divided by 0.26, which calculates to approximately 0.3077. Now that we have set up the scenario with our witness, let's walk through the mathematical breakdown step by step to find our answer. As you will see in the next slide, this result might be quite surprising given how reliable the witness seemed. Conclusion: forensics. So, let's take a moment to reflect on our results from the forensics example. Looking at our final calculation, we can see that even though we have a witness who is 80% reliable, the probability that the car is actually blue is only about 30.77%. Now, this might feel quite counterintuitive at first glance. You might be thinking, if the witness is mostly correct, shouldn't the probability be higher? However, the reason the probability remains so low is due to the base rate we discussed earlier in the medical example. Because blue cars are relatively rare in this city, making up only 10% of the total population, the sheer number of non-blue cars means that even a small error rate from the witness can lead to a high number of false alarms. As we move into our next slide, we will look at how to avoid these types of logical pitfalls in your own calculations. Common mistakes to avoid. First, the most frequent error I see is confusing the probability of a given B with the probability of B given A. It sounds subtle, but it is fundamentally different. Let's look back at our medical diagnostic example. The probability of a positive test result given that the person actually has the disease, which we write as P of positive given disease, is simply the accuracy of the test. However, what we are actually trying to find is the probability of the person having the disease given that they have already received a positive test result, written as P of disease given positive. One is about how good the test is, the other is about the actual health of the patient. Never swap these two. Second, please be careful not to ignore the prior probability. In our previous slides, we saw how the rarity of a disease or the low percentage of blue cars heavily influenced our final answers. Beginners often focus only on the new evidence and forget to include the base rate or the initial probability of the event occurring. If you leave out the prior probability, your calculation will be mathematically incomplete and your result will be incorrect. Finally, watch out for calculation errors in the denominator. Remember, The denominator in our formula represents the total probability. It is the sum of all the different possible paths or scenarios that could lead to our observed event. When you are working through these problems, ensure you have accounted for every single possibility in that sum. If you miss even one branch of the probability tree, your entire calculation will be off. Now, before we wrap up today's lesson, I want to pause and discuss some common pitfalls. As we have seen through our examples in medical testing, manufacturing, and forensics, Bayes' theorem can be quite counterintuitive, and it is very easy to make a mistake if you aren't careful. Keep these 3 points in mind, and you will be well on your way to mastering these practical applications. Key takeaways. All right, we have reached the end of our lesson. Let's take a moment to consolidate everything we have learned today through our various examples. First, let's revisit the concept of reverse logic. Throughout our session, whether we were looking at medical tests, factory defects, or eyewitness testimony, we weren't just calculating forward probabilities. Instead, we used Bayes' theorem to work backward. We started with an observed effect, like a positive test result or a defective bolt, and used it to find the probability of the underlying cause. Second, I want to emphasize the role of priors. This was the most crucial takeaway from our medical and forensics examples. You saw how the initial probability of a hypothesis, which we call the priori probability, can completely shift our final conclusion. Even with a highly accurate test, if the initial prevalence of a disease is very low, your final result, or the posteriori probability, will remain low. Never ignore that starting. Finally, let's look at a structured approach for your future problems. To avoid the common mistakes we discussed in the previous slide, I want you to follow this consistent 4-step framework whenever you face a practical application. Step 1. Identify the partition. This means clearly defining all the possible mutually exclusive causes, which we can label as E1, E2, and so on up to En. Step 2. Identify the observed event, which we will call A. This is the evidence or the result you have actually seen. Step 3. Determine your probabilities. You need to find the prior probabilities, which are the probabilities of each cause, written as P of E subscript I, and the conditional probabilities, which are the likelihoods, written as P of a given E subscript I. And step 4. Apply the formula to find P of E subscript I given A. This is where you plug everything into the theorem to find the updated probability of your cause, given the evidence you've observed. If you follow this structure, you will be able to navigate even the most complex probabilistic scenarios with confidence. Great job today!